Hello students, this is Mridul Agrawal. I've done my MTech from IIT Mandi in Mechanical Engineering with a specialization in energy systems, and I've been teaching since 2017 onwards. I've taught in various schools and coaching centers, and then I started my teaching career in FITG Limited, and then currently I'm teaching at ICAD School of Learning, Nagpur. So today we'll be discussing about the calorimetry, and we'll be discussing the concepts related to the calorimetry in some basic part, and then we'll be solving one and two problems based on it. Okay, so let's start with some introductory part. let's say we have uh, let's say we have a container like this. Okay, and you have got some tea inside it. Okay, some tea inside it. Now we know that the temperature of the tea is generally higher than the surroundings, and let's say the temperature of this tea is 35 degrees Celsius, and you are sitting in winter, so let's say the temperature of outside is 10 degrees Celsius. Now what will happen? You know that after some time the tea will cool out. When the temperature of the tea, you see, goes down, then the heat is transferring from the tea to the environment. So definitely there is some heat transfer from the tea to the surroundings, due to which the temperature of the tea goes down. And the temperature of the tea goes down from, let's say, 35 degrees Celsius to, let's say, 15 degrees Celsius, and finally to then 10 degrees Celsius, because you know that the surroundings is at a bulk temperature of 10 degrees Celsius. So the tea has to maintain a temperature of 10 degrees Celsius in order to have no heat transfer at the equilibrium condition. So what is an equilibrium condition? When the temperature of the system and the temperature of the surroundings becomes equal, then there is no heat transfer involved in between the two systems, and in such a case what we say is that the body has got the temperature equal to the surroundings, and the thermal equilibrium has been achieved. The thermal equilibrium has been achieved. Okay, so you know about the temperature. What is temperature? Temperature tells you the degree of temperature tells you the degree of hotness and degree of coldness. Degree of hotness and degree of coldness of a body. Degree of coldness of a body. For example, if we consider, let's say, a very hot iron bar, then its temperature can be as high as 1500 degrees Celsius. So when you measure this physical quantity, you know that the temperature of the body is very high, and with the help of the temperature you can quantify how much is the heat content, or how much is the degree of hotness of this body. Similarly, when you take ice, then you take the temperature of around 0 degrees Celsius, or minus some degrees Celsius, let's say minus 3 degrees Celsius or minus 4 degrees Celsius. Then you say that the body is having a lower temperature. So depending on the temperature of the body, you tell the degree of the hotness and the degree of the coldness of the body. Okay, so when there is a temperature difference, as you can see in the tea and the surroundings example, that the tea is having a temperature higher than the surroundings, and it is 35 degrees Celsius, and the surroundings temperature is only 10 degrees Celsius. So what happens? Actually the heat transfers from the higher temperature body to the lower temperature body by itself. You don't have to put any external energy to transfer the heat from tea to surroundings. You just have to see that whatever body is at higher temperature, that body will lose heat, and the body at lower temperature will gain heat. So the body at higher temperature will lose heat to lower down its temperature, and the body at lower temperature will gain heat to maintain an equilibrium at the final condition. Okay, so how do you quantify the amount of heat? So you know that when there is a temperature change involved, when there is temperature change involved, let's say delta T, then whatever heat is absorbed by a system, that brings a change in its temperature, And how do you quantify the heat absorbed? That heat absorbed by the body is equals to the mass of the body times the specific heat capacity of the body times the temperature change that has occurred in the body. So M denotes the mass of the body. This is the mass of the body. Okay. S is the specific heat capacity of the body. Specific heat capacity of the body. And delta T is the temperature change of the body. Temperature change of the body. Okay. So when there is a temperature change occurring in a body, then you quantify the heat absorbed as ms delta T, where S is known as the specific heat capacity. And what will be its units? So you know that heat absorbed is in joules, mass is in kilogram, and temperature is generally considered in Kelvin. So the specific heat capacity will have the units as joule per kg Kelvin. Okay, so always it is not important that whatever heat is absorbed, it will go into the temperature change of the body. Sometimes what will happen is whatever heat is transferred to the body, that goes into the phase change of the body. So whatever heat is absorbed by the body, that goes into the phase change of the body. For example, if a body is at a 0 degree Celsius, so it will be, let's say water is there, so it will be in the format of ice. When this 0 degree Celsius ice gets converted to 0 degree Celsius water, then some part of heat must have been absorbed by the body. And in such a case, what has happened is the temperature of the body has remained constant, but the phase change has occurred in the body. So the if the body has occurred a change in phase, or a body has undergone a change of phase, then whatever heat is absorbed by that body is given as the latent heat. So we call it as a latent heat. So during the phase change, during the phase change, during the phase change, whatever heat is absorbed or released or released, that goes into phase change, goes into phase change. Okay. So it is not important that always the body will get a temperature change when the heat is transferred to it or heat is lost by it. It may also happen that the phase change of the body has occurred. Okay. So let's discuss more on these concepts. Uh, Pretty importantly, we know that sensible heat. What is sensible heat? Whatever heat that is required to raise the temperature of the body, whatever heat is required to raise the temperature of the body, that heat is equal to the sensible heat. That heat is known as the sensible heat. And how it is calculated? So this Q denotes the energy, M denotes the mass of the body, S denotes the specific heat capacity of the body, delta T is the temperature change that has occurred in the body. Similarly, what is latent heat? Whatever heat is required by a body to bring a change in the phase of the material. For example, the ice at 0 degree Celsius gets converted to 0 degree Celsius water, or 100 degree Celsius water gets converted to 100 degree Celsius steam. So whatever heat that you have given is, that heat is known as the latent heat. So Q denotes the latent heat, M is the mass of the body, L is the latent heat of vaporization or fusion per kg for a body. For example, if we know that we have to calculate the latent heat. What is the latent heat? So latent heat is Q by M. So it is the heat required to bring the phase change, divided by the mass for which the phase change has to be occurred. Mass for which the phase change has to be occurred. And this latent heat can be latent heat of fusion as well. Latent heat of fusion as well. Latent heat of fusion as well. When the body is getting converted to, let's say, 0 degree Celsius water to 0 degree Celsius ice, then whatever heat that you have to extract out from that body is known as the latent heat of fusion. So for water it is 80 calorie per gram. Okay. And latent heat of vaporization. What is latent heat of vaporization? Whatever heat is required to convert 100 degrees Celsius water into 100 degrees Celsius steam, that heat is known as the latent heat of vaporization. And what is the value for this? For water, it is 540 calorie per gram. 540 calorie per gram. So during the phase change, you have to remember this, that during the phase change, the temperature of the body will remain constant. All of the heat that is absorbed by the body goes into the transformation of the phase of the body. That doesn't go into the temperature change of the body. So let's say you have a water. I'm taking the example for the water, and you plot the temperature versus heat graph like this. Now what we see at 1 atm pressure, we see that the temperature of the body increases up to 0 degrees Celsius. So this is 0 degrees Celsius. At 0 degrees Celsius, the temperature remains constant. When you give more heat, the temperature rises, and then again it becomes constant at 100 degrees Celsius. At 100 degrees Celsius, the temperature again becomes constant. And at 100 degrees Celsius, you have to give 540 calories per gram in order to convert it into steam. And then you finally again increase the temperature of this body. So you can observe that the temperature of the body has remained constant at 0 degrees Celsius at 100 degrees Celsius when the body is undergoing the phase change. And when the temperature of the body is changing, then you can see that you are giving the sensible heat. So you can see that there is a phase change over here at 0 degrees Celsius uh, ice to 0 degrees Celsius water. So this is the latent heat of fusion that is required. Now from third point to fourth point, that is the at 100 degrees Celsius water to 100 degrees Celsius steam, you have to give the latent heat of vaporization, and its value is 540 calorie that I have told you, and this is 80 calorie per gram for ice. Okay. You have to also remember the specific heat capacity during the temperature change. So for the temperature change occurring between minus some degree Celsius to 0 degree Celsius, let's say for ice, then the specific heat capacity you generally take for water as 0.5 calorie per gram Celsius, and for water you take it as 1 calorie per gram degree Celsius. And you know that 1 joule is equals to 1 joule is equals to 1 by 4.18 calorie, or you can simply say that 1 calorie is equals to 4.18 joule. So this values you have to remember. And what is the water equivalent of a substance? Let's suppose you have a substance like this. Let's say you have a body like this A, and you have to find the equivalent amount of water. What How will you calculate the water equivalent? So let's consider you give the same amount of heat, and it has a specific capacity of SA. Let's say the body A has a specific heat capacity of SA, and the body that is water is having the specific heat capacity, you know this as SW. Now you bring the same temperature change in the two bodies. Now if you bring the same temperature change in the two bodies, then whatever amount of water that is required in order to bring the same change in temperature, when the same amount of heat is given, that amount of water will be known as the water equivalent of the substance. So mw into sw into delta t must be equal to mv, mass of the body, into specific heat capacity of the body, into delta t. So mass of the water that is calculated from this equation is mb into sb divided by sw. So this tells you the water equivalent for this substance, let's say body A or any body B. So this is known as the water equivalent of substance. So what is the definition of for this? It is the equivalent mass of water that would require the same amount of heat energy as the given substance to achieve the same temperature change. So you have to bring the same temperature change, you have to give the same amount of heat, whatever amount of water would be required to get the same. So now we'll be discussing a problem based on the calorimetry, and we'll be discussing in a good detail so you are able to understand this problem. So let's say we have a question like this. Two liquids at temperature 60 degrees Celsius and 20 degrees Celsius respectively have masses in the ratio of 3:4, and their specific heats is in the ratio of 4:5. If the two liquids are mixed, then find the resultant temperature of the system. So let's say I'm drawing a diagram so that you are able to understand what is the situation like. So let's say you have two liquids. So the liquid having higher temperature would be at the upper surface, let's say 60 degrees Celsius, and the liquid at the lower temperature is colder, so it will be in the bottom. Now what will happen is, when the two liquids are mixed, what will happen, you understand? Let's say this 60 degrees Celsius body is placed with a 20 degrees Celsius body. What will happen? The heat will transfer from the 60 degrees Celsius body to 20 degrees Celsius. So the heat is lost by the 60 degrees Celsius body, and the heat is gained by the 20 degrees Celsius body. So whatever heat is lost by the 60 degrees Celsius body is the heat that is gained by the 20 degrees Celsius body. So let the final temperature of the two bodies become same, and that is equal to Tf. So you know that that whatever heat is lost by the 60 degrees Celsius body, that is gained by the 20 degrees Celsius body. So let's write the given quantities first. So you know that the temperature initially is 60 degrees Celsius for the first liquid. For the second liquid, the temperature is 20 degrees Celsius. Final temperature is, let's say, Tf. Now masses, the ratio of the masses is given as m1 by m2 is given as 3:4. Their specific heats ratio is given as s1 by s2 equal to 4:5. Now what we know is that the heat is lost by the 60 degrees Celsius liquid. So heat lost by the 60 degrees Celsius liquid is equals to the heat gained by the 20 degrees Celsius liquid. So how you calculate the heat lost by the 60 degrees Celsius liquid? So it is equals to the mass of that liquids, let's say m1, then specific heat capacity is s1, and it is losing the temperature, so it is 60 minus Tf. That is equal to the heat gained by the 20 degrees Celsius liquid, so that would be m2 into s2 into Tf minus 20. Now we know that m1 by m2 and s1 by s2, these two ratios are given in the question. So this is equals to Tf minus 20. Now m1 by m2, you know this from the given quantities, that is equal to 3 by 4. S1 by s2 is equals to 4 by 5, and that is 60 minus Tf, and that is equals to Tf minus 20. So 4 gets cancelled, so it is 180 minus 3 Tf equal to 5 Tf minus 100. Now we take the 100 on the left hand side, so it gets 180 plus 100, and minus 3 Tf on the right hand side, it goes 8 Tf. So 8 Tf is equals to 280. So Tf becomes 35 degree Celsius. So you have understood that the final temperature of the two bodies would be 35 degrees Celsius, because you know that 60 degrees Celsius body is losing the heat, so it is going to 35 degrees Celsius, and 20 degrees Celsius body is gaining the heat, so it is going at 35 degrees Celsius. Hope this problem is clear. Let's take another problem. Let's say you have a condition like this. The temperature of the equal masses of three different liquids A, B and C are 12 degrees Celsius, 19 degrees Celsius and 28 degrees Celsius. So the masses of the three substances are same. Let's say M1, M2, M3. These are same. The temperatures are given as T1 is given as 12 degrees Celsius, T2 is given as 19 degrees Celsius, T3 is given as 28 degrees Celsius. Okay, so 1 is A, 2 is B, and 3 is C. Okay, the temperature when the A and B are mixed is 16 degrees Celsius, and when B and C are mixed, it is 23 degrees Celsius. What will be the temperature when A and C are mixed? Definitely when A and B are mixed. When A and B are mixed. Let's take this situation. Are mixed. Then what will happen? When A and B are mixed, then A is at temperature of 12 degrees Celsius and B is at temperature of 19 degrees Celsius. This is B, this is A. A is gaining heat to go to the temperature 16 degrees Celsius and B is losing heat to go to the temperature 16 degrees Celsius. So whatever heat is lost by B, that is the heat that is gained by A. Heat is lost by B. What is the heat lost by B? So that is MB into SB into 19 minus 60. And what is the heat that is gained by A? That is equal to MA into SA into 16 minus 12. So that is equals to, since the mass is same, specific heat, let's say, of B is S2. So it is S2 into 19 minus 16 is 3. That is equals to M1 S1 into 16 minus 12. So what is 16 minus 12? That is equal to 4. Now masses are same, so we have cancelled it. So it becomes 3s2 equal to 4s1. So this is the first equation. Now when let's say you mix B and C, when B and C are mixed, so what will happen? Let's take the initial temperature down. So uh, when B and C are mixed, then we know that B is having a temperature of 19 and C has a temperature of 28. B has a temperature of 19 and C has a temperature of 28 degrees Celsius. So that 28 degrees Celsius body will lose heat to go to the temperature 23 degrees Celsius, 23 degrees Celsius, and 19 degrees Celsius body will gain heat to go to the temperature 23 degrees Celsius. So the heat lost by C is equals to heat gained by B. So what is the heat lost by the C? That is equals to mass of C, that is the same as mass of B. So M into S3 into 28 minus 23, that is equals to M into specific heat capacity for B is S2 into 23 minus 19. So it goes as S3 into 5 equal to S2 into 4. So this is the second equation. Now we know that we have to calculate what will happen when A and C are mixed. So when A and C are mixed, what will be the final temperature that you have to calculate? So A is at a temperature of, we know that A is at a temperature of 12 degrees Celsius and C is at temperature of 28 degrees Celsius. So A is at a temperature of 12 degrees Celsius, C is at a temperature of 28 degrees Celsius. Let me check that. Yeah. Okay. So we have A going to some temperature, let's say T, and C going to some temperature, let's say T. But definitely what will happen when A and C are mixed, then C will lose heat and A will gain heat to come to a temperature T. So the heat is lost by C. It is lost by C, and that is equals to the heat gained by the A. So heat is lost by the C. What is the heat lost by the C? That is equals to M into specific heat capacity of C, that is S3 into 28 minus T, that is equals to heat gained by the A. What is the heat gained by A? So mass of the body into specific heat capacity of the body 1, and then it is going to temperature T, and this is 12. So we have S3 by S1 and S3 by S1 into 28 minus T equals to T minus 12. From 1 and 2 equation we can calculate S3 by S1. So we know that from second equation, from equation 2, we have S2 by S3 going as S2 by S3 as 5 by 4, and from equation 1 we have S1 by S2 going as 3 by 4. S1 by S2 is 3 by 4. Now if you multiply these two terms, then what will happen? Then you will get S1 by S3 as uh, S1 by S3 as 15 by 60, and you can insert this value over here to get your required condition, but you have to actually reciprocate it. So that is equal to 16 by 15 times 28 minus T equals to T minus 12. So once you calculate this, that comes out to be 20.25 degrees Celsius, and this is your final answer. So you can definitely see that when you are getting a temperature of 20.25 degrees Celsius, then definitely A is gaining heat and C is losing heat to come to a temperature which is common for both. Hope this problem also is very much clear, and this lecture you must have been very familiar with. Hope to see you in your next class, and we'll be discussing more and more problems and more questions based on it. Thanks.